I know people are still coming in, but I'm going to get started. So welcome everybody to the third in a series of three klogW talks celebrating our GSNP's newest fellows. Today we are going to hear from Srikanth Sastry, and I will introduce him in a second. I just want to say the two previous talks were recorded and the recordings will be uploaded onto the GSNP klogW website, which is shown here before March meeting, hopefully. So just a couple more announcements. Oops. We encourage everybody, if you're not already a member, to please join GSNP. And if you are a member of GSNP and are going to the March meeting in Las Vegas next month, we'd like to invite you to the business meeting and reception, which will take place Tuesday evening at 6:15 p.m. in room 125 at the Convention Center. And you can hear about all the activities of GSNP and also about, it will be an opportunity to vet our fellows in person. Srikanth, you'll be there?
Yeah, I'm planning to be there.
Yeah. If you're not a member and would like to join, if you go to engage.aps.org, you can click on this button that says join GSNP. And the last thing I want to do before I introduce and then turn it over to Srikanth is just some Zoom etiquette, which you're probably all very familiar with now after 3 years of doing this. But during the talk, please make sure you're on mute. The way we'll do questions is during the talk, you can post questions in the chat. And if there are questions of a clarificatory nature, I will interrupt Srikanth and ask him those questions. But if they're broader questions that you would prefer to ask in person, you can either leave them in the chat or unmute yourself and ask at the end. So I'll call on you to ask questions at the end. And I would appreciate it if you could raise your virtual hand so I can call on you in the order you raise your hand. And with that, let me stop sharing the screen. And so today we are delighted to have Srikanth Sastry telling us about yielding and fatigue failure in amorphous solids. So Srikanth, or Shri as he's often called, is a professor at the Theoretical Sciences Unit at Jawaharlal Nehru Center for Advanced Scientific Research in Bangalore. Shri got his bachelor's degree from Bangalore itself, the National College, and a master's degree from IIT Bombay, from where he recently received a distinguished alumnus award as well. He got a PhD from Boston University and has been at JNC since 1998 after doing postdoctoral work at NIH and Princeton. Srikanth and I overlapped at TIFR Center for Interdisciplinary Sciences in Hyderabad for a year and a half. Since then, he's gone back to JNC. He has received a number of awards before this one. He has, aside from the one I mentioned from IIT Bombay, he got the Shanti Swarup Bhatnagar Award in 2008, the C.V. Raman Young Scientist Award. And he is a member of all three national academies in India. Yes, there are three. The Indian Academy of Sciences, the National Academy of Sciences, and the Indian National Science Academy. He is now also a fellow of the American Physical Society, and his fellowship citation reads for pioneering quantitative investigations of energy landscapes, dynamics, and thermodynamics of supercooled liquids, network forming liquids and glasses, for novel insights into the role of geometry in shear jamming of grains, and into yielding transitions and memory formation in amorphous solids. And that citation sort of covers all the areas that Srikanth is well known for. And we hope to hear about some of those today. So Srikanth, the floor is yours.
Thank you very much, Shubha, for that kind introduction. And I'm happy to be here giving this talk on the occasion mentioned. Is my screen now fully visible?
Not yet, so you need to share it.
Oh. Ah. Okay. Ah. I thought I had it all under control. What do I do? I'm sorry about this. I'm sorry. So how to do this on the Zoom icon, right? Yeah.
Do you see the, maybe you escape the full screen mode in Zoom and maybe that will help. We did have it up 5 minutes ago.
Yeah, I'm sorry about this.
No.
But what's going on? I'm not finding the. All right. Yeah. Here we go. Share. Yeah. No, I think I got it now. Is that good?
Yes.
Okay, great. Yeah, I apologize for that. Okay, so yeah, it's a pleasure to speak to this audience. As Shubha mentioned, the sort of several problems related to the transition from fluid to rigid states of matter that I have been involved with, which are nicely captured in the jamming phase diagram. But I resisted the temptation to start with that. Instead, I'll focus on basically the behavior of glasses, and in particular the mechanical behavior of glasses or amorphous solids. I'm going to sort of broadly divide what I'm going to tell you into three parts. One is talking about simulations of glasses under cyclic shear deformation. And I'll explain why that's interesting as I go along. And I'll talk about how one might go about modeling yielding behavior under cyclic shear. And finally, I'll talk about some recent work on a phenomenon called fatigue failure, which is something that is very familiar from everyday life, but is also, it turns out, closely related to the problem of yielding under cyclic shear. Fatigue failure, just to say in two words, is a phenomenon where a solid fails after a number of repeated applications of external stress. Okay, and this number of cycles of loading depends on the magnitude of the deformation in interesting ways that I'll come to at the end of the talk. So this work has been done over some years, but I will confine everything that I'm going to sort of focus on beyond the introduction to work that's been done during the pandemic years. So here are some publications that that have arisen out of this work. It's been done in collaboration to a considerable degree with Himanshu Bhaumik, who was a postdoc with me at JNC ASR and who's currently at Technion. Other simulation work has been carried out by a postdoc, Shivkumar Atani, and more recently by Swarnendu Maiti, both at JNC. Giuseppe Fofi at Orsay, Mohitin Mungan at Bonn, Jack Parley, and Peter Solish at Göttingen have been great collaborators and parts of the work. Okay, so I went through this outline of the talk already. So let me just begin by sort of saying a few words about glasses, and my purpose here is not really to give an introduction to glasses and the glass transition, but simply to point out that a large number of materials exist in the glass or amorphous solid state, or disordered solid states. And the fact that these materials are microscopically disordered implies that you have a large number of possible microscopic arrangements that are frozen in, even when the macroscopic properties are kept fixed somehow. So the fact of having a degeneracy of microscopic configurations is sort of intrinsic to the problem of studying amorphous solids. And that's really the point that I would like to emphasize by through this slide. And now, on the other hand, the properties of glasses do depend on the method of preparation. So in addition to the microscopic structure being different when the macroscopic properties are the same, the macroscopic properties themselves of the glass of a given substance change depending on how it is prepared. Okay, and this is going to be a recurring theme in what I'll talk about. And in trying to sort of understand the behavior of such materials which can possess a large microscopic degeneracy, even when the macroscopic properties are fairly well defined. And also, to think of these being solids, one takes recourse to an energy landscape picture where one imagines that a given material has the possibility to have many locally stable structures, and concretely, and certainly in the computer simulations that I'm going to be talking about, these are local energy minima or inherent structures, as they're called. But one could also, depending on the context, think of them as free energy minima or metastable states, etc. I won't go into those details today. The central concept in thinking about these kind of pictures is what's called the configurational entropy, which I won't have occasion to sort of talk about directly, but the configurational entropy is a measure of the multiplicity of locally stable structures, and one therefore has in mind a distribution of states of different energies and properties. And this idea is certainly going to be very relevant for what I'll be talking about. And as I already mentioned, one can access different states depending on the method of preparation. And in particular, if one were to sort of anneal the glasses better, that is to cool it more slowly, one accesses in this picture deeper energy minima, and these are what I will be referring to as more stable glasses. Okay, so better annealed, more stable, or poorly annealed and less stable glasses. Okay, so coming to the mechanical behavior of amorphous solids, of any kind, solids, amorphous or crystalline solids, when they're subjected to small external deformation or stresses, they respond elastically. That's what makes them solids. These responses are characterized by finite elastic moduli, and one thinks of the behavior as being reversible. The removal of the stresses will restore the original configuration of the system. Larger stresses lead to plasticity and yielding and failure. These are irreversible behaviors, and here are some examples of such irreversible behavior, which sort of illustrates that they're of obvious importance to the use of these solids as materials. And so beyond sort of the straightforward rationale of characterizing these amorphous solids as materials, there is a wider range of phenomena. I've listed a few examples here, such as disordered magnets, front propagation in disordered media, granular matter, landscapes and avalanches, earthquakes, where very similar ideas and questions are relevant. Okay, so now when one thinks of the mechanical response of crystalline solids, one has a language in which to talk about it, which is that plastic response in crystalline solids arises as a result of the movement of well-defined defects, the dislocations, and here is a little cartoon movie to illustrate what I'm talking about. And these are both well-defined and observable, and therefore there's at least an initial point from which one can talk about plasticity in crystals. Close to the point of failure, the things do become more complicated even for crystalline solids, but at least one has a clear idea of what the defects are that are relevant. We're interested in the corresponding picture for amorphous solids, and here there isn't anything as well defined as dislocation defects, but we do understand some things. Plastic rearrangements, when one considers whether a solid or a crystalline solid or an amorphous solid, are reflected in stress drops, such as what I've shown here in the graph, where the y-axis has stress and the x-axis has strain, and these corrugated stress-strain curves illustrate the presence of many, or indicate the presence of many plastic rearrangements. And these stress drops in amorphous solids correspond to local rearrangements of particles. These are referred to as shear transformation zones. And the video on the right bottom illustrates what one might be thinking about. As strain is applied, you see that there's a local region of space which undergoes a rearrangement that is not consistent with the global strain that is being applied. Now, when one such local transformation takes place, and if one imagines the rest of the system as being an elastic or a linear elastic medium, one has an understanding of what happens. And this is going back to the work of Eshelby, one expects that such localized rearrangements will lead to a propagation of stresses which are long-ranged and have a particular form that has been both observed in computer simulations and experiments, and therefore fairly well understood. And these stress fields can lead to interactions between different parts of the system and trigger other events away from the site of the initial plastic event. And how this leads to yielding behavior is something that one would want to understand. Okay, before I continue, so I'm essentially going to be talking about mechanical behavior as represented by the left bottom curve here, where I'll be looking at stress as a function of strain. But what this figure here shows is that if one applies a large enough deformation beyond the yielding point, which is sort of visible through a drop in the stresses beyond a maximum value, one settles into a steady flow regime, and correspondingly there is a steady state stress. Now, what's important for a lot of rheological studies of soft matter are the steady state stresses as a function often of shear rate, and that's shown on the right hand graph, where one is looking at the shear stress as a steady state shear stress as a function of shear rate. I won't be talking about that part of flow behavior much, but I will be interested in how, as the deformation is increased, one goes from sort of a linear elastic behavior to an elastoplastic flowing behavior. Okay, now there are many ways in which people have tried to understand this kind of flow behavior and rheology, and I want to mention just sort of one example, which both relates to what I said earlier about the energy landscape picture, and also will relate to some of the results I'll talk about later on. So this is something called soft glassy rheology, SGR, and this is based on the Bouchot trap model, which is a schematic landscape model to capture some aspects of glassy behavior. The trap model assumes an exponential distribution of energy minima, and activation out of these minima, or activation can bring the system out of any of these energy minima, and the excited system can fall back into any one of the available other minima, and this leads to, in this thermally activated version that was originally studied by Bouchot, interesting relaxation dynamics. But one can sort of think of adding to the thermal activation a second perturbation, which is due to externally applied strain or stress. And if one imagines sort of doing it at a steady rate as a function of time, the strain pushes the system up in energy, as illustrated here in the middle row of graphs. And the top row aims to sort of show some real space picture of what might be happening in the system. And basically, when one reaches some kind of a threshold energy, one then becomes unstable, or the minimum in which the system is residing becomes unstable, and you make a transition to a new minimum, and this new minimum has a minimum energy at the strain at which this transition took place, and therefore is a stress-free new state of the system. Okay, and this model has been studied extensively to understand complex glassy rheology by the original group of people, including Peter Solich, Mike Cates, Suzanne Fielding, and so on. Okay, I'm going to come back to that picture of how to think about sort of the rheological and yielding behavior of glasses. But first, let me say a little bit more about the kind of questions we want to address. So one key question that I'm going to be thinking about is the manner in which the yielding behavior of a glass might depend on the degree of annealing with which I have prepared it. So here is a graphic from a review by Nicola et al. From a few years ago, which sort of illustrates one part of this, which is to show that when one is talking about amorphous solids, there is sort of a whole range of things that one could be talking about, from molecular glasses such as metallic and silicate glasses, polymer glasses, colloidal glasses, foams, etc., etc. And each of these have somewhat different yielding and rheological behavior. And the question that one could be addressing is, can we understand this diversity in a simple manner? And one possible handle is to think of these as glasses or amorphous solids that are, in some definable sense, differently annealed and correspondingly have different yielding behavior. What I show in the graph in the middle right is from computer simulations, the stress strain curve of glasses prepared on the computer, one set of which are not so well annealed, and these show basically a gradual increase in the strain, or rather the stress as strain is increased, going over to some flow value. In comparison, a better annealed glass exhibits an overshoot. So the stress goes up higher than the flow value, and then there's a stress drop going over to the flow stress value. And so a glass that is prepared by fast cooling will show the first kind of behavior, whereas a glass that is prepared with slow cooling will show an overshoot.
Srikanth, there's a clarificatory question in the chat
Okay.
from Greg Huber.
Yeah.
Coming back to the trap model, when you say an exponential distribution, do you mean that the probability to find a trap of depth between h and h plus dh is proportional to exponential of negative h over kt dh?
Right, that's correct, and that's the original Bouchot trap model. But there's no. I mean, one doesn't have to stay with that distribution of minimum values. In fact, in what I'm going to be talking about later, I'll be using a Gaussian distribution. Okay. But before we get to that, let me tell you a little bit about computer simulations, which have been used to investigate yielding behavior in amorphous solids, and this has been done quite extensively. And so these simulations perform both uniform shear deformation, such as what I just talked about in the previous slide, but also cyclic shear deformations. And further, one can sort of do these deformations under athermal conditions or at finite shear rates and finite temperatures, etc. So in this talk, I'll describe results from cyclic shear deformation of glasses, largely under athermal conditions, though I will talk under athermal quasi-static conditions, though I'll talk about finite shear rate simulations later on. So what distinguishes cyclic shear from possibly from uniform shear deformation is that you apply your deformation repeatedly over many cycles, and this leads to the properties of the glasses evolving and reaching steady state values. So for a given amplitude of deformation, you have sort of a steady state ensemble to think in terms of as giving you the behavior of the glass. And broadly, there are two sort of regimes to this steady state behavior. In the first regime, after some number of cycles, during which there is plasticity and rearrangement and reorganization of configurations of atoms or molecules, you reach a state which doesn't change anymore from cycle to cycle. So you go through sort of a limit cycle, and these are called absorbing states. And the other behavior is described as diffusive, and look stroboscopically the cycle at where the particle positions are. These particle positions evolve in a diffusive manner. Okay, so absorbing states correspond to glasses below yielding, and diffusive states correspond to yielded states. Okay. Sorry. Yeah. So just to so I mentioned athermal quasi-static deformation. And just to say 2 words about it, what one does in this procedure is to subject energy minimum structures to shear deformation, and one applies a shear strain, and the resulting deformed structure is subjected to energy minimization. And so this produces a sequence of configurations that are always energy minima. And when one does that, you have there is an elastic part of the response where the energies and the stresses change continuously, which are interrupted by discontinuous changes, which correspond to plastic rearrangements. Okay, and these again are illustrated by the stress strain curve that I show here. Okay, so this is sort of a more graphic illustration of what is happening. So if you imagine that in this simple cartoon, your system is capable of being in a sort of a one of 2 minima in a bistable system. Your shear deformation tilts this landscape so that the initial minimum that you may be in becomes unstable, and you go over to the other minimum, which will eventually become unstable, but not at the same point as when the first minimum became unstable. And this leads to a situation where the state of the system at a given strain value depends on the history. Okay. Okay. Now, so here is sort of a thumbnail sketch of what we do in our simulations. We study a number of different model glasses, and using the athermal quasi-static shear procedure and the cyclic shear deformation is illustrated by this video clip, where one goes from 0 strain to a maximum strain, back to 0, and then to a maximum negative strain, and back to 0. And this cycle is repeated again and again. And one typically studies the properties of configurations at the end of each cycle. Okay, so what happens when one does this repeatedly? If one looks at the potential energy per particle as one quantity to monitor, there are 2 regimes. As I mentioned, in the first regime, the final energy that I reach after a number of cycles depends on the strain amplitude, as I show here. So I'm getting to lower and lower energies with increasing strain amplitude, but it also depends on the initial state, and the final energies that I reach have memory of my initial state, so I don't go into any kind of an ergodic situation. On the other hand, if one is looking at sufficiently large strain amplitudes, then regardless of what initial state that I start with, I end up going to the same final state. Okay, and this final state now has energies which increase with the amplitude of the strain that I apply. And in between these 2 regimes is the yielding transition. And And one interesting thing which you can sort of read off from these graphs, which is going to be relevant for the later part of my talk, is that the time it takes to reach these steady states is a non-monotonic function of the strain amplitude, which appears to diverge at the yielding point. Okay. Okay, so this I will say very little about, but this is just to sort of flag the fact that a lot of what I've been talking about under cyclic shear has resonance with some work that started several years ago, looking at athermal colloids that are suspended in a viscous fluid, which are subjected to oscillatory deformation. So there too, you find a transition between an absorbing and a diffusive state and a divergence of a time scale to reach steady state values. And in the absorbing phase, one has interesting memory effects. And these kind of reversible, irreversible transitions have been studied under a variety of systems with connections to the physics of jamming, yielding, and memory. I won't have time to talk about any of these things, but these have all been looked at, including by us, and are very interesting. Okay, now.
Srikanth, quick clarificatory question. When you're talking about two minima, this is just because you're looking at the initial and the final state and the energy minima relative to those?
No, that was just...
it was just illustrative.
That was just an illustration when you have a bistable system. But you know, you'll have very many local minima that are possible. And so again, as a simple thing, you can think of basically a configuration space that is sort of a multiplication of all these two-level systems. This is, in fact, something that's used in analyzing memory effects. It's called the Prezard model. But these different local two-level systems do interact, and that leads to even more complex behavior. Okay. But that was just an illustration.
Yeah, thanks.
Okay, so now let me come to sort of something that I've mentioned from the beginning, which is the importance of annealing or the stability of the glass on the yielding behavior. And this I show here under cyclic shear, where on both the left and the right panels, what I'm showing are respectively the energy and the stress, maximum stress that is reached at the end of the kind of transients that I talked about here. So if I keep sort of watching, eventually I reach some final energy or stress, and I'm plotting those in this graph as a function of the initial energy of the glass as well as the strain amplitude. Okay, so what one finds when one starts with very high energy or poorly annealed glasses is the behavior that I already indicated, which is that the energies of these glasses with an increase in the strain amplitude go to lower and lower value till they hit the yielding point, and then they go on to higher values beyond the yielding point. And the curious thing is, regardless of which initial energy over a certain range that I start with, I always converge to this asymptotic sort of energy before I yield. Okay, so this is already very interesting. But if one looks at deeper energy minima or better annealed glasses, the behavior changes completely. So below this red line that I have on this energy versus strain amplitude plot, there isn't much happening to the energies of my glasses till some strain amplitude at which I exhibit a discontinuous change. And this discontinuous change becomes bigger and bigger as I go to lower and lower energy or better annealed glasses. And the same kind of behavior is exhibited by the stress strain curves, where my stress overshoots as well as the drops to the yielded state in the stress increase with an increase in the annealing of the glasses. And these drops, as I'll come to in a little bit, are always accompanied in the case of cyclic shear with the formation of shear bands. Okay, now what is this threshold energy is an interesting question. And we don't have very clear answers at this moment, but one analysis that we made shows quite clearly that the nature of the energy landscape is changing at the threshold energy we found by considering yielding behavior. So at this energy that corresponds to the red line, one has the vanishing of the saddle index of the nearest saddle points from typical liquid configurations. Okay, so this is a very suggestive connection to glass physics, which needs to be explored further, but I won't talk about this now. Okay, and this is just to quickly show that the same kind of sort of change in the yielding behavior has also been studied under uniform shear deformation. Okay, now how does one go about modeling this behavior? As I already mentioned, one can sort of think of plastic response as being composed of plasticity within a small region or volume of the glass that I'm looking at, and a long-range propagation of Eshelby stresses. And so a good description of the local plasticity combined with the well-understood propagation of stresses should therefore give you a model description that faithfully captures the mechanical behaviors of glasses. So the goal is to basically build these models of local plasticity that are good enough to do the job. So here I describe very briefly a picture that one can have. As I've already mentioned, even if I were to look at a sub-volume of a glass, the configurations of atoms in that sub-volume will correspond to a large number of possible energy minimum configurations. And each of these I'm going to call a mesostate. And so each of these local energy minimum structures, I can think of taking and deforming it by applying external strain. And under such strain deformation, I will have an increase in the energy of the system because there is an elastic energy that I'm adding. And but there will be a limit of stability beyond which I will undergo a plastic deformation. And then I have to say what happens when a given minimum becomes unstable. And like in the SGR model, one can sort of say you go to any other minimum that is present in your description or in your distribution, which has at that strain value a lower energy, okay, which is sort of simple enough. And so I won't sort of describe the model in more detail. In some limit, it reduces to the SGR model. But basically, the essential ingredients are a distribution of energy minima, a description of how the elastic energy changes, which is basically like a simple quadratic form, a specification of the stability interval in strain over which a given minimum or a mesostate is stable. And here the key ingredient is that this stability range is assumed to depend on the depth of the minima. Okay, so with these, one can then sort of look at the kind of behavior that emerges, and the specific thing that I show here is to start with minima of different depths and ask if I apply shear deformation of a certain amplitude, what happens after some large number of cycles of such deformations have been applied. And so this, the big left graph shows the final energies that I get after, I think in this case, 1,000 cycles of shear have been applied. And what one sees in quite a striking way is that this yielding diagram looks very similar to what one finds in computer simulations. And it's remarkable because this is, when I talked about sort of making these elastoplastic models, I talked about mesoscopic blocks, and what I'm giving you is a description here of one of those blocks. I didn't really talk yet about interactions between the different blocks. So what I have is a one-site model, but this one-site model already captures a lot of the features that one sees in computer simulations of glasses, and including the fact that if one is looking below the yielding transition, the number of cycles it takes to reach the final energies or the final state is a very sharply increasing function of the strain amplitude, but it never diverges. There is no genuine transition in that sense. Okay, now in order to try and understand why one finds this kind of a behavior of the time scale required to reach the final state, one can ask a very simple question, which is, if I start with a mesostate of a certain energy and I apply one cycle of strain, what energy do I end up with? Okay, and in the simplest case, if nothing happens, and this is true for very deep energy minima, the final energy is the same as what you started with. Okay, and this is observed in these color maps by these red diagonal lines where the initial energy and the final energy are the same. Okay, and now when you go beyond a certain value that is of the initial energy that is fixed by the amplitude of the strain, what one finds is that one makes transitions stochastically to different energy minima, and these energy minima have, or mesostates have, energies that are distributed roughly insensitively with on the initial energy. So in other words, regardless of what the initial energy is, after one cycle, I find myself in a final energy which is taken from essentially the same distribution. Okay, so with this distribution, and also recognizing that out of these different energies that I reach at the end of a cycle, some states which are the higher energy states will undergo further transitions in the next cycle and the next cycle, whereas the ones that are below will not anymore undergo transitions because they're stable with the amplitude of deformation that I'm applying. I can then understand the result that I obtained for the time scale, that the time it takes for me to reach a final state. And basically it has to do with the fact that as I apply larger and larger strain amplitudes, the number of states that are available that will be stable with respect to that amplitude is a drastically decreasing function. And as a result, the probability that I'll make a transition to one of those states in a given cycle is smaller and smaller. And therefore, it takes me a longer and longer time in order to reach a final state, which is stable with respect to the next cycle of deformation, and I can sort of then turn it around and say, if I've applied a certain number of cycles of deformation, what is my amplitude of strain beyond which I have yielding? And this is basically related to this number of cycles, or the time that I've observed the system for. And so I get an estimate for an observation time dependent yield amplitude, which is a fairly slow function of the number of cycles. But one can actually do better, as I will explain in a minute. So I can take this idea that there is some...
Before you go on, sorry. So there was a question in the chat again about this relaxation time scale. Is it obtained from an inverse of the probability of getting trapped in a minimum, or is it something else, like a multidimensional Kramers? No,
that's basically what it is.
Okay.
Yeah, and so it's a trapping time, right? So that becomes more clear by this sort of further simplification of the description I make of the dynamics. I imagine that I have some, if I didn't have this trapping feature in my dynamics, I imagine that I have some invariant distribution that I can think of as being a result of a confining potential. And but in addition, I have a certain value of the energy of my state at which I get absorbed, because the energies beyond that red line that I've shown correspond to states which are stable under the deformation that I'm applying. And so this is then like a simple stochastic model of a random walker in a potential subject to an absorbing boundary at a value which is specified by the amplitude of shear that I'm applying. So this leads to a yielding diagram, very much like what I have shown before, as well as an estimate of the yield strain amplitude, which is looking a bit more complex, but it basically also has the same dependence that I already mentioned down here, where something is wrong. Okay, it's basically like a fourth power or 1/4 power of the logarithm of time, which is what you see here as well. But one can do better than this, right? And the idea is simple. So in the simplest description, I'm saying once I reach a low enough energy for a given strain amplitude such that I'm stable with respect to one cycle of shear, then I stay there forever. But one can certainly on physical ground say that that's not entirely true, because I could have activated processes because of which, even if I'm sitting in one of those stable minima, I can escape with a certain probability. And if one puts in this possibility of an escape and with a characteristic escape time, one can sort of redo this calculation and one finds that the yield amplitude now is really properly fixed, not by the observation time, but by the escape time. Okay, and one can go a little bit further and ask for what the escape time would be if one considers not only transitions between the yielded and the absorbing states and the reverse at a given rate given by the inverse of an escape time, but one considers the entire spectrum of states that are below and allows for transitions between them. So one can then calculate an escape time, which is a strong function of the yield amplitude. Interestingly, the trapping time, as I told you already, is a strongly increasing function of the strain amplitude. The escape time is a strongly decreasing function of the strain amplitude. The crossing of these two effectively gives you the yield points. But it also, as I've shown here, if I ask what is the probability asymptotically of being in the absorbing or the yielded state, they are very, very strong functions of the strain amplitude, but it's not a perfectly sharp transition. And this is because in the picture that I have, I'm thinking of the escape probability as being thermally induced, but in fact, in a lot of the models of the kind I'm actually about to talk about in a minute, what one has is a picture where the noise that leads to activation arises from plastic activity, mechanical activity elsewhere in the system, and therefore there's a feedback, and this feedback leads to the possibility of diverging escape times, okay? And at a sharply defined yielding transition, but it also will tell you that above that yielding transition, there is an escape time that's a strongly decreasing function of the amplitude of deformation. And so the next question we've been asking is this a useful way of thinking about fatigue failure? And I have to tell you what that is. Fatigue failure is basically the phenomenon where materials subjected to cyclic loading fail after a certain number of cycles, which number increases with decreasing applied stress or strain amplitude. And these are represented in so-called Wöhler plots or SN diagrams. And so on the y-axis here is the stress amplitude that you're applying, and the x-axis is the number of cycles that you need before you fail. And what you show, what you see in this diagram in the blue curve is that there is a stress amplitude below which the number of cycles needed to fail diverges. Okay, it's not drawn in a very nice way, but you can make a comparison with what we've discussed earlier, where we said that under cyclic shear deformation, the number of cycles needed to reach the steady state diverges at the yielding transition. Okay, so there's sort of a couple of associations one has to make. So the number of cycles that I need to reach the steady state, I should think of as the failure time, and I should also then think of what I've been calling the yielding strain amplitude or the yielding point as the fatigue limit. That is this limit, or it's called the endurance limit in this sketch, below which failure does not happen. Okay, so with that, okay, and I'll come back and continue on that in a minute. But the other thing that we've done is to sort of take the same one state or a microscopic description, and then to write sort of a dynamical equation for the probability distributions of states, which I won't have time to say more about, but basically here you have a term, which is the last term here, that basically tells you that if your strain reaches a certain threshold value, that minimum becomes unstable. And then there is the second to last term that tells you that with an aggregate rate, which is represented by this quantity y, you create new states which with a certain distribution. But there's also a diffusion term, which has, again, this y term, which is sort of a total measure of activity, which is how many states are becoming unstable at a given time. And this controls the diffusion coefficient, okay, in this Fokker-Planck equation. And so with this description, one can go ahead and look at sort of where the stability boundary is. And there's this additional parameter alpha, which also controls the diffusion coefficient. And with respect to the strain amplitude and alpha, one can construct the boundary between the frozen and the yielded states. One can also numerically obtain a yielding diagram, which once again looks for what we've seen in simulations and in these standard models. But here is the interesting thing. If one looks at the activity as a function of the number of cycles at different applied strain amplitudes, there is a range of amplitudes over which this activity is non-monotonic. So it begins to decrease. And if you're below the yielding point, cyclic shear yielding point, it goes all the way to 0. But if you're slightly above, it decreases very much like what would happen below the yielding point. But then at some point, it kicks up and goes to a finite value. And this upturn signals the failure event in this system. One can therefore look at the number of cycles to failure. And one finds, as some people have found in literature recently, an exponential dependence of this failure time at sufficiently large amplitudes above the yielding point, but close to the yielding point, a power law dependence with an exponent of -1/2. Okay. Now, this is the kind of behavior that's very much seen in computer simulations. So the next 5 minutes, Shubha, is that okay? I'll spend on describing, going back to simulations and describing some of the results that we have. So what I show here are results from AQS simulations at a number of different strain amplitudes, starting with very high initial energies. And what one finds is this curious behavior, focus on the green curve here, where the energy sort of goes down as, you know, indicating that the system is getting annealed because of mechanical deformation, up to a point, something happened with these highlight circles, up to a point at which a sudden up jump in the energy indicates that the system has yielded. And this kind of behavior is also visible at other strain amplitudes, which are bigger, and it happens at an earlier time. And so this seems to suggest that, you know, there are two parts to the response of a glass. One is mechanical annealing, and this is always something that happens. And in addition, there are these failure events that are triggered somehow, and this is something that we don't yet have a very good handle on. And these are very sudden events at later times, okay? And this description of fatigue failure appears to be very different from what people seem to say in literature. And I say this with a little bit of hesitation because I'm not completely clear what picture people have in the materials community, but there is sort of a description of failure in terms of damage accumulation, which seems to suggest that it's a gradual process. So from one cycle to the other, you accumulate damage, and this leads to failure eventually. Okay, this doesn't look like what you see in amorphous solids. I'll skip this, except to say that when you have these sudden jumps in energy to the yielded state, these are accompanied by the formation of what are called shear bands. Okay, this you see on the right side pictures or videos in this panel. So we've been recently looking at all these phenomena using finite shear rate simulations. And once again, to illustrate what I said, these already these sudden jumps in energy are accompanied by the formation of shear bands. And these are shown also in this video, where the graph shows the amount by which particles move over a given cycle. And you see the emergence of this peak in the red curve at the point where the energy begins to jump. Equally interestingly, there are structural changes you can monitor, and these have clear correspondence with the behavior of the energy and the formation of shear bands. So one can look at data like this, and one can ask, can I identify a failure time? And roughly speaking, the midpoint of this sigmoid-shaped curve is what I identify as my failure time. I do this using the energy Q6, which is a measure of the structure, and it's sort of telling you that it's becoming less ordered as the number of cycles proceed. And also D2 min, which is a measure of the amount of plasticity that you have, which is increasing as a function of the number of cycles. And so I can, for each of these quantities, compute a typical time, but also a width over which this transformation happens. Okay, this is sort of illustrated here. I'm running out of time, so I won't, unless somebody asks me, I will skip this for the time being. I can also look at the amount of displacement of particles from one cycle to the other as a way of identifying where the yielding transition is. And I'm not quite sure why. Yeah, some things have moved around a little bit. These vertical arrow lines are supposed to point to where there's clearly a transition in the behavior, which is the yielding amplitude of 7.1%. So one can now look at the failure time as a function of the amplitude of shear deformation, and ask, does this sort of obey any of the forms that people have discussed earlier? One such form is the exponential form, and this was actually, in fact, even seen in the mean field theory, but we don't find that to be a valid description, nor do we find what's called the Basquin form, which is a simple power law with respect to the strain amplitude. That's sort of valid in some limited range of strains, but as I get close to the fatigue limit or the yielding point, I have a stronger divergence. What seems to be a good description is a power law, but with an exponent that's considerably larger than what we found in the mean field theory. Okay, so here is something of a surprise. We've also been looking at the width of the transformation zone or in time. And it turns out that for the smaller of the system sizes that we have been simulating, these widths scale linearly with the failure time, which is something that I at least was not expecting. And this seems to be, needs to be understood better in terms of its significance, because the transitions, whenever we look at data like this, appear always to be rather sharp, and therefore one needs to understand the meaning of the width scaling with the failure time. But one indication that that story is far from complete is when you look at larger system sizes, one has widths that scale with the failure time, but with a much smaller power. Okay, so this is an issue that needs to be sorted out. So the summary of the results for fatigue failure are that analysis of models suggests that fatigue failure involves competing processes of annealing and activated escape and exhibit interesting non-monotonic behavior. This picture appears different from conventional descriptions of fatigue failure as arising from accumulation of damage. But investigation of models cannot yet precisely describe the instability that leads to failure. and the role of cooperativity, and that's something where we have to do more work. Preliminary investigation of simulation data reveals indeed the presence of non-monotonic change, but the failure events appear to occur over time windows that scale with the failure time, which is a little confusing. And so we have more work to do to come up with an appealing description. Here is a summary of everything that I've said. I won't go through all of this, except I'll sort of summarize things where we still have to understand better, and where the open questions are. One thing that microscopically one should understand better is the dependence of the stability intervals in strain on the degree of annealing of glasses. The other question is the meaning of the threshold energy, and the divergence of timescales near the yielding transition have some level of explanation, but not really a very appealing and compelling one. Now, one thing that I didn't emphasize, but it did come up, is that there are sort of fairly significant entropic effects that are associated with yielding, and this needs to be brought out more clearly, and we need to have a better understanding of the mechanism of fatigue failure and the role of interactions that lead, for example, to the formation of shear bands. Okay, with that, I thank you for your attention. I seem to have run a little bit over time. I apologize for that. And thanks.
Thank you, Srikanth. Yeah. So questions from the audience, just raise your hand and unmute yourself and ask. Yes, Ezekiel.
Hi, Sri. Thank you for the very nice talk. So you have been doing both molecular dynamic simulations of extended systems and then this elastoplastic model of one elastoplastic block, no? And with one side, you already recover a lot of the features. But my question is, what are the things that this one side approach is missing, and what are the things you think we should explore more with extended elastoplastic models in three dimensions?
Yeah, so basically, there are a couple of interesting things. I mean, one is clearly the formation of shear bands. And what does that mean in terms of the role of cooperativity in the yielding transition? And it seems that it should be a cooperative. The failure event is cooperative, but I don't understand very well how to think about it. And the other, and of course, in the kind of elastoplastic models, the spatially extended versions that, for example, you guys have worked on, you do reproduce the formation of shear bands, but I'm not sure if there's a clear understanding of what triggers their formation. The other question that's to me is interesting is when you look at sort of these failure events, starting with fairly high initial energies, you find that you continue to have annealing in the rest of the glass after yielding, after the formation of shear bands. And so this is an interesting phenomenon. This is something that you see in computer simulations as well. And this is something that needs to be understood better. But mainly, I mean, in terms of my own focus right now, I mean, one comparison one can have in mind is nucleation. Do you think of failure as a nucleation event? What is nucleating? Why is it nucleating? So these are things that I would like to understand better.
And sorry, a related question. Have you ever seen in molecular dynamic simulations the formation of more than one band? But it's always only one.
We haven't, but Vishwas, that you know, has done simulations where he sort of does simulations with a sufficiently large aspect ratio, a very long box, where he does see multiple shear bands, and they seem to have interesting dynamics of formation and attrition, which again, if one wanted to sort of think in nucleation language, have echoes of post-fall ripening. So it looks like eventually one band will win from what Vishwas has done.
Thanks, Srikanth. Walter?
Sri, you are mentioning the meaning of the threshold energy. So is it too naive to say that it's just the temperature of mode coupling theory? Because that's basically where the geometry of the landscape changes.
Well, that's what I said in the slide. I didn't say it in words. It is the mode coupling. Yeah. So, I mean, this threshold energy is, as I said, the crossover temperature associated with the mode coupling, where the saddle index vanishes.
But for your toy model, what is then the interpretation of it?
So this is the part that's confusing, because in the toy model there is no, in the landscape that I assume there is no special energy. So it somehow emerges, and my best guess at this point is that in the model you're assuming something about the stability range of a given meso state as a function of the energy, and my belief is that will actually dramatically, so I'm assuming in the toy model that it's a linear dependence, but I think that dependence will be much more dramatic in real glasses, and that might be the explanation.
Okay, thank you.
Alexander?
Thank you. It's a fascinating talk. I was intrigued by your statement about the failure. Now, in real failure systems, once something is broken, it's actually broken, right? In your simulation, presumably, if things fail and you just stop your simulation, they'll heal completely, right? And you'll be in a new minimum, and you can do this all over again, right? I was wondering if you could comment on the difference between those systems, and where in many of these systems that people talk about failure, this more complete failure comes from, and how that relates to what you're seeing here.
Right. So, one thing that I did highlight to some extent is the fact that the mechanical deformation in a cycle of shear has as one primary consequence the formation of better annealed structures. Okay, so you could call it healing, and now in the limit that I'm studying, which is the athermal limit, there is no temperature, so the healing will not happen by itself. But presumably, if you do have finite temperature glasses, the aging dynamics will lead you to healing over time. And so this is sort of the competition that one needs to understand, because the mechanical perturbation involved in cyclic shear can either anneal the glasses, but if the amount of plastic activity as a result is too high, you undergo yielding, right? Now I mean, you said something about other contexts, which I'm not sure I quite understood. But in sort of trying to understand fatigue failure, I mean, there's sort of work by Hans Hermann and his colleagues from several years ago, where somewhere they remark that experimentally people do understand that healing is an important part of the story, but I haven't sort of really seen a good explanation of how people think about it.
I think the point I was trying to make is you were mentioning that there is this understanding that some failures that come from the accumulation of failures, and so that the more you operate it, you have these failures that build up, and then they eventually lead to breaking, which is different from what you're seeing in these experiments, right?
Mm-hmm.
But if you think about these systems where you have, well, where people have this model of additional movements leading to more breakage, you also have situations where the material that you break, so and that's something well, if you have a macroscopic glass, like an actual glass, and you break it, right, just putting it back together does not heal it somehow, right?
No.
Whereas in your simulations, presumably, if you have glass bits, you put them back together, they'll heal, right? And so there's something else going on there. That was just the thought that I had.
Yeah, no, so I actually in fact, something that I thought was quite dramatic in our computer simulations is if you sort of perform, so if you take a shear banded or yielded glass, but if you perform cyclic shear at sub-yielding amplitudes, you do see you do see healing, right? I think in terms of the comparison with experiments, you never quite, when something breaks, there's also a volumetric effect. Things move away. There's a crack formation rather than yielding in the sense that I'm talking about. But in systems where you form sort of these shear zones, but there is cohesion still, I would expect healing very much to be possible. Like in more soft classes, I think it should be possible.
Great, thank you.
Other questions for Srikanth? So, Srikanth, I had a quick clarificatory thing. So the difference between the damage accumulation models and the fatigue failure that you're talking about is the lack of annealing in those, that there is no healing behavior happening?
Yeah, I think in terms of picture, definitely that's a key difference. Like I said, even in the models by Hermann and company, they sort of mention the healing part very parenthetically, but it seems to be a key element in how their models work as well. Yeah, so that is, yeah. But I've tried to talk to some material scientists to ask, what does this word mean? And I don't think I have a damage. I mean, so I think when you have things happening on a meso to macro scale, you do see sort of, I mean, you can see cracks in micrographic images, and you can see comparable things in amorphous solids, but I'm not sure at least at the microscopic level at which we're looking, what's the right picture to have. So this is still, like I said in the beginning, it's work in progress. We don't fully understand.
Well, so if you want to hear more from Srikanth, please come to the March meeting, business meeting, and go to his talk and all the other talks that GSNP is sponsoring. Srikanth, thank you very much for a very nice seminar. Thanks everyone for coming.
Thank you very much. It was a very nice opportunity to talk to all of you.